Okay, this is a setup that I've put together to show you the frictional behavior of a pipeline. I've got 3 of these blue pipes in series. They attach with T connections, and at each T connection there's a piezometer that goes vertically up. The water comes from this container up here that is attached to the control valve, and it's on top of 2 Aqualibrium stands that I put on top of each other and then attach them to the frame of the whiteboard. You can use anything you like, but make sure it's sturdy. You don't want this to fall on anybody. The water is then attached to the bottom of the tank. It comes down to the valve here. Right, let's open the valve and see what happens. Okay, so this is beautiful. It shows us the hydraulic grade line in the pipe. This is, you can see how the hydraulic grade drops. You can see it's pretty much a straight line, is what we expect. Now the water runs through the pipes and then out at the end here, I've lifted it a little bit before it goes out. And that is to make sure that the pressure, the reading on the piezometer is high enough that we can get a proper reading. This is a U-tube which I cut open just to ensure that you don't get air trapped that can disturb the flow. And then the water goes in here. In here we've got a pretty hefty pump. It's a standard pond pump, but a pretty hefty one. And this takes the water up through the back and into our big tank again. You can also connect this to the municipal water supply and take this outlet to the drain, but then you can't color the water. So this is my preferred option. We can use this setup to show the different components of the Bernoulli equation, which I've written down here. Now the Bernoulli equation gives us the 3 components of mechanical energy in a fluid. And it's got the 3 components are Z there, which is the elevation, P over rho G, which is the pressure head, and V squared over 2G, which is the kinetic energy, and we call that the velocity head. So let's show those components on at this point in the pipeline. So the first component is the Z component, which is the elevation of the pipe above our datum level. So it's really at that level there, and so that is our Z component. That's, in this case, 10 centimeters. The second component is our pressure head, and this is shown above the pipeline by the level in our piezometer here. So up to that level there, that is going to be our pressure head. So if I draw a line down here, that is going to be P over rho G, and that's about 60 centimeters. And so what's missing still is the kinetic energy, the velocity head, and for that we need the velocity in the pipe. Now to get the velocity, we need to measure the flow rate. And we can do that very simply using a container with a certain volume and a stopwatch. I've got them here. So very simply, we're going to move the flow in there, start the stopwatch at the same time, and measure a certain volume and a time. And from that, we can calculate what the flow rate in the pipe is. And if we've got the flow rate and we know the diameter of the pipe, we can then calculate the velocity. So I've already done the calculation, and the velocity in this pipe is about 1 meter per second. And so V squared over 2G is about 5 centimeters. And so we can plot 5 centimeters above this point would be there, and that's going to be the total energy in the system from our datum level. Now, what I'm going to do next is just take my pen and I'm going to mark all the hydraulic heads for each of these piezometers. There. And then I'm going to take this ruler and we're going to connect them all. This might not be easy. Okay. Now, I can't reach all of them, but they're pretty much in a straight line. So I'm just going to connect this in a straight line. This will go up to the point up there. And this is called the hydraulic grade line. The energy line, what happens to the total energy, will follow the hydraulic grade line because we have a constant flow rate throughout the system. We have a constant diameter throughout the system. And so conservation of mass tells us that the velocity has to be the same throughout the system. In other words, we're going to have this 5 centimeter velocity head above the hydraulic grade line at all these points, and we can use our ruler to draw a line that's 5 centimeters above the hydraulic grade line. And this is the energy grade line. So we've got the hydraulic grade line here, and we've got the energy line. Now, when we look at the system, we see that if we look at the whole pipe from the first piezometer to the last piezometer, and we want to look at the energy losses in the system, the elevations are the same. So the Z components don't change, and they are constant in the energy equation. The velocity we've already established is the same everywhere, so the velocity energy stays the same. So the only place where energy can be reduced in the system is the pressure, and that's exactly what we're seeing. That it's a pressure that is reducing as we have energy losses in the system. Now, if we take the energy, the pressure head or the hydraulic grade at the start here, and we draw a line horizontal line on the board. Let's try and do that. So try and get that horizontal. So this is the starting hydraulic grade of the system. And then this is the ending hydraulic grade at the end of the pipeline. And so this distance here is the energy loss, or HF, in our system. And so we can directly measure the energy loss in the system. We know the length of the pipe, and that'll allow us to transfer this to the Moody diagram and calculate the roughness of the pipe.